Yeah, welcome everybody. And yeah, as Joseph said, we are very happy to have Sherwood giving a talk for us today. So I've known Sherwood for a while. So he was a PhD student at Caltech. And during his PhD, he wrote, as far as I know, the first open source Neutrino Transport code, Monte Carlo, and made it publicly available. So that's a great contribution. And after that, he did postdocs at North Carolina State University, and now he's a postdoc and, in fact, an NSF postdoctoral fellow at the University of California, Berkeley. And in recent years, he's been focused on understanding the neutrino flavor transformation in core collapse supernova and neutron star mergers. And today, he's going to talk about modern neutrino physics in supernova and neutron star mergers. So welcome, Sherwood.
Thank you very much. Yeah, so I was told that there's a wide variety of people from different backgrounds in physics that could attend this talk. So please do feel free to interrupt and say that doesn't make sense, or you're using jargon that people in condensed matter don't use. So yeah, just let me know. I'm happy to stop and chat about things. So yeah, in the past couple of years, I've been mostly interested in trying to understand what exactly neutrinos do in these violent cataclysmic events, neutron star mergers and core collapse supernovae. So throughout this talk, I'll be talking mostly about neutron star mergers, but all the physics, of course, applies to supernovae as well. I'll touch a little bit on the supernovae. So just so that we're all on the same page, I want to establish what the whole hullabaloo is with neutron star mergers in the first place. So a neutron star merger, what I actually mean by that is a neutron star merging either with another neutron star or a black hole, and following an extended period of a slowly decaying circular orbit. So when this orbit decays and the two compact objects actually collide, one or both the neutron stars is tidally shredded, sending a bunch of very neutron-rich matter out largely in the equatorial direction. And then what is left over is some central compact object, either a black hole or some hypermassive neutron star, and around it some accretion disk that's moving at a good fraction of the speed of light. And this accretion disk is largely cooled by neutrinos, and the dominant stress that's causing the matter to accrete is magnetohydrodynamic stresses. There's also association between relativistic jets and neutron star mergers. So either by magnetic stresses or some neutrino annihilation mechanism, there's thought to be some relativistic jet that's formed in the polar directions. So the reason why these are so interesting is because they're tied with a lot of mysteries, a lot of open mysteries in the universe. So first of all, one of them is just a general interest in transients. There's a lot of stuff when we look up in the sky. Things flash, things explode, and we want to know what exactly is happening. And there's a huge variety of these things. This is an image of the only, to date, the only confirmed kilonova that was from 3 years ago. But there's a whole lot of other stuff happening. It's not just supernovae and kilonovae. There's a lot of different things. So this is a chart of the time scale and brightness for various kinds of events. So you see core collapse supernovae and 1A supernovae are up here. And they're relatively bright, which means you can see them with a lot of different telescopes. And they the time scale that they decay on is pretty long. And so that means that even if you don't catch it right when it happens, if you look a couple of days later, it'll still be there. So they're a lot easier to find. So as you go toward this shorter time scale and lower luminosity, things get harder to find. And that's why at this point, kilonovae are significantly faster. So a kilonova is what astronomers call the optical part that we see that comes from neutron star merger. But so these are a lot faster and a lot dimmer. And so they're a lot harder to find, which is the reason why to date there's only one certain detection along with a couple of other candidates. So this is the one certain detection. There's a lot of observations and a lot of different bands. Pretty much every telescope on the planet looked at it. But we're hoping to get more of these in the future so that, and also continue exploring more of the dimmer and and faster transients to discover other things that are out there that we just haven't had the depth of perception and the rate of surveying the sky to discover these things yet. And kilonovae are part of that puzzle. The second major thing that they're involved in is trying to understand the origin of all the stuff around us. So we're commonly told that we are all made of star stuff, and what that's commonly interpreted as is core-collapse supernovae explode and send a lot of this star matter, iron and calcium and oxygen, all these other things, out into the galaxy to be reprocessed into new stars and planets. But there's a limit to what elements can form in supernovae, and if you're more involved in this research, also like AGB stars and a few other, and cosmic rays and a couple of other things that form these elements. But if you look at the very heavy elements, which are the ones I'm showing here with atomic mass numbers larger than, somewhere around 100, then these elements can't be formed by the processes that form all these elements that get ejected from neutron star mergers, or sorry, that get ejected from supernovae and from stars. And so you need a fundamentally different process to create them. And so it's known that you can create these elements if you have a huge number of neutrons. The idea being that if you have some seed nucleus that's sitting in this dense bath of neutrons, the seed nucleus is going to get riddled with neutrons faster than it can decay. And so you end up with this very large, very neutron-rich atomic nucleus, which eventually decays back down. And so by riddling these nuclei with neutrons that quickly, you can build up a whole spectrum of very large elements. And that's this R process, that R is for rapid neutron capture, R process pattern that you see in the sun in these black dots here. And so there's a few features that people generally talk about. There's a couple of peaks where you have overabundances of various elements, which come from various properties of the nuclei. And then what's particularly important in our case is these lanthanides here, which have complicated atomic shell structures and therefore lots of lines for photons to interact with. And so if you create a lot of these lanthanides, there's a large opacity. And so that changes how any of these transients look, because it changes how the photons diffuse through it. So there, even before the detection in 2017 of a kilonova, there are lots of clues that say that these heavy elements can't be caused by supernovae. This is one example of one of these clues. This is a plot of each of these points is a star in our galaxy. And on the x-axis is the amount of iron in the star relative to hydrogen relative to the sun. And on the y-axis is the amount of europium. If you were to plot this same plot in calcium, for instance, then this correlation would extend down to very low metallicity stars. Metallicity being the amount of hydrogen, or the amount of iron. So for elements that are formed in supernovae, this trend continues downward. But for these R process elements, there's a bunch of scatter here, which says that so for supernovae that make both iron and calcium, you expect that correlation. But because there's all this scatter that doesn't correlate with the supernova formed elements, you expect that these elements like europium are not formed by supernovae, because if they were, you would expect them to track the other supernova formed elements. So there are a lot of clues saying that these elements come from neutron star mergers. And this is particularly interesting for observations of neutron star mergers, because like I said, if you produce a lot of these elements, it's very optically deep. So this is the mass, this is a theoretical result showing this is time and brightness. So the neutron stars merge and emit a bunch of light, and the brightness of the event slowly decays over a matter of days. If you don't have many of these heavy elements, it happens pretty quickly. If you have a lot of these heavy elements, it happens much more slowly and is much dimmer and much redder. This is also mediated by neutrinos. I'll get back to the impact of neutrinos in a bit, but yeah, neutron star mergers are intricately tied to we think, intricately tied to how these heavy elements are formed. Now, I should say it's still not certain. It's still not certain where all of these first peak elements come from. It's entirely possible that there's a number of different sources that provide these elements, and we don't know that it's only neutron star mergers, and we don't know how much of these elements got produced in this very detailed observation of neutron star mergers. So these are still things that people are actively working on. Another long-standing mystery that neutron star mergers are connected to is the origin of short gamma ray bursts. So these, as the name suggests, are very short, like less than a second bursts of gamma rays, which come from extragalactic sources. And this was a long-standing mystery for a long time. But we now know that there's statistically a connection between short gamma ray bursts and neutron star mergers. And furthermore, this is these are observations of the afterglow from the jet formed from GW 170817. And from these observations, you can say that because it's increasing in time for the first 100 days or so, you know that we weren't looking directly at the jet, and this break tells you something about the opening angle of the jet. So we now know that there was a jet that was formed in the neutron star merger that we observed, and so it's there is a connection between neutron star mergers and short gamma ray bursts, but how that energy is actually generated, how all that energy is collimated into a single direction, these are still active questions that people are trying to work on. And finally, neutron star mergers are one of the channels that that form black holes, and so it's currently an open question as to how a lot of the larger mass black holes formed. How, you know, whether some of these are formed inherently in the early universe, or how smaller objects combine to form larger black holes. This pathway is still poorly described, and neutron star mergers are part of this picture. So there's a lot of mysteries that neutron star mergers are associated with. But one of the problems with all of this is that when we try to understand neutron star mergers, there's as of now, relatively little that we can see. There's a lot of circumstantial evidence. Astronomers are great at finding circumstantial evidence and combining these into insightful deductions. But if we really want to understand the details of what's happening, it's rather complicated. In particular, the neutrinos are especially complicated. So the neutrinos are the weakly interacting fundamental particle that dominate the thermal evolution of the disk and the hypermassive neutron star. So after the neutron stars emerge and there's this hot accretion disk around the black hole or hypermassive neutron star, the disk and neutron star are hot enough that they are rapidly emitting neutrinos, which cool the disk. But these neutrinos are also changing the relative amounts of neutrons and protons. So the original neutron star matter is, of course, a bunch of neutrons, so it's very neutron rich. And so what these neutrinos tend to do is drive this distribution of matter from very neutron rich to more even distributions of neutrons and protons. And like I said, if you change, if you remove a lot of these neutrons that are used for generating these rapid neutron capture processes, you change what kind of elements get formed in the ejecta, which changes the opacity of the ejecta, which changes what the ejecta looks like. There's also, it's also possible that there may be enough power of neutrinos being emitted that collide with each other and annihilate in the polar regions, and it's possible that they generate enough energy to drive a relativistic jet. So like I said, it's still not well understood how all of this energy is generated, and so neutrinos may be an important part of that picture. So neutrinos are intricately tied to these mysteries as well, and so we need to have a detailed understanding of what these neutrinos actually do in neutron star mergers to really have the complete picture of how neutron star mergers work and what they mean about the evolution of elements and all these other mysteries. So the goal, of course, is to really deeply understand everything that's going on inside the neutron star merger. We want to know how the outflows are launched, when a black hole is formed, what the ejecta looks like, And of course, I can't see my own slide. Oh yes, new physics. We want to know that if we look at it at a neutron star merger and we have all the observational clues from the gravitational waves and the gamma rays and the photons, and if we're really, really lucky, something close by enough to see neutrinos, we want to know whether we're seeing new physics. What we want to do is model these systems with all of these standard physics that we know, and if we want to get to the point where we can compare the observations with the models that we have and decide and show how all of these things work, and show if the models don't match the observations, we want enough fidelity to say there's some physics that we're missing. So what's required to do this is a whole lot of interesting physics. We need general relativistic magnetohydrodynamics because the disk is dense enough and conducting well enough that the magnetohydrodynamic approximation is very, very good. And it's the magnetic stresses that drive the accretion into the black hole. We need a nuclear equation of state to describe the properties of matter at and above nuclear densities. And we need a detailed description of radiation transport to describe both the transport of the neutrinos through the system and the photons through the ejecta to understand the light that we actually see. And this is just an example of a simulation from Davridice showing this is the central black hole, and for instance, this panel is the density. So you have a dense disk you're looking edge on and a largely evacuated polar region. And so the idea is that if we can simulate these, we should, if our equations and our numerical methods match nature, what nature does, then we can get back what nature's telling us. Of course, in order to understand nature, nature isn't going to pick one kind of neutron star merger to do. It's going to put together whatever neutron stars and whatever black holes it wants to, and it's going to use whatever fundamental microphysics it has that we don't currently understand to create its neutron star merger. So what we really want to do is do a large number of simulations to map out what each of these different things do and be able to take some kind of observation, map it back to what's really happening inside. And so this is, for example, something that Rodrigo has done recently, doing simulations, in this case, looking at the different masses of the disk and the central compact object, and showing what that implies about the ejecta. But we also know that the models that we have aren't yet perfect. And arguably, they may never be perfect, but we know that they're currently insufficient. So on the right here is a plot of, so these purple dots are, again, the solar abundances of these heavy elements. So abundance is a function of the mass of the element. And the three different lines are the results that come out of three different simulations that are identical except for the treatment of the neutrinos in the simulation. So this orange curve is a leakage scheme, and then this is a M0 scheme with assuming some equilibrium, and an M0 scheme with the light blue line. And so it's especially for these light heavy elements, the first peak elements, there's a huge impact of the neutrinos. And so we really want to have a adequate treatment of the neutrinos to have a good understanding of the elements that come out of these mergers. So here's my outline. Congratulations, you got through the first part. Hopefully I convinced you that the details of the neutrino transport really are intricately tied to many of these fundamental mysteries in astrophysics. So for the rest of the talk, I will talk a little bit about the neutrino transport problem itself, and describe exactly how difficult of a problem it is and what we can do about it. And then I'll go on to talking about some more interesting neutrino physics involving the flavor transformations between different neutrino flavors. Between each of these, I'll stop and encourage people to ask questions or say something didn't make sense if that's the case.
Sherwood, is it just me, or is there's a gray bar that's
on the top left?
Yeah.
Yeah, that's my Zoom thing.
So that does cover up sometimes some of the titles.
Okay, how do I get rid of this?
Now it's on the right.
Yeah, maybe I'll just move it so that I can see. So yeah, I don't know, unless somebody, a Zoom expert, knows what to do about it.
Yeah.
Okay.
Well, you can tell if it's covering something up then.
Yeah.
Yeah, like it is.
We can interrupt more if it blocks something. That's
okay,
important.
great. All right. So let's talk about neutrino transport. So that is understanding precisely how neutrinos move around and carry around energy and lepton number in these simulations. So the Boltzmann equation is the equation that describes all of this, and it's on the surface very, very simple. So the idea is that you have some distribution function which describes how many neutrinos in each location are moving in each direction. And as this DFD lambda says, it's the change in this distribution function as you move along the path of the neutrino. If there were no collisions, if this right-hand side were 0, then as you move along the path of neutrino, obviously the number of neutrinos going along that path doesn't change because nothing's moving them. But if you do have collisions, then the number of neutrinos moving in that direction changes. So the real hard work in simulating this is expanding this derivative. It has a time and a spatial component, and writing out the multidimensional integrals that go into this collision term. So one way to do this is to treat it and to do a Monte Carlo method, where this entire left-hand side is treated by representing this distribution function as a large number of individual particles. And these particles will move along their own trajectory as particles naturally do, and they will be emitted and scattered and absorbed just like ordinary neutrinos would be. And if you simulate a large enough number of these, you get a good idea of what's moving on, or what's going on.
Is this non-relativistic then?
This is actually completely relativistic, general relativistic.
Okay, and where does that, like, is that inherent in the Boltzmann equation, or does that come in with some of the collision terms?
It's inherent in the Boltzmann equation if you write the Boltzmann equation relativistically. So that's why I do this DFD lambda. Lambda is an affine parameter along the geodesic of the neutrino.
I see. Okay, got it.
Yeah, but the collision integral, generally what you have to do is you transform into a local co-moving orthonormal tetrad so it looks just like regular Minkowski space, so you don't have to think about all the relativistic stuff for the collision term, because you just transform into that diagonal space.
Thank you.
Mm-hmm. And yeah, so like Rodrigo mentioned, I have this code Sidonu. Now it's Sidonu GR, which is open source. It takes some snapshot and uses Monte Carlo methods to calculate what the radiation field looks like. So the way that we do this is we take some background. In this case, it's some three-dimensional general relativistic simulation of a neutron star merger. And so what comes with that is the density, the temperature, the electron fraction, all of the metric quantities. And based on that, you calculate the emissivity everywhere, and you spawn a given neutrino in a random location with a random direction, just like a regular neutrino would be. And you let the neutrino move a random distance. In this case, it moves a very small distance until it scatters next, according to the scattering opacities. You let it keep scattering around and advecting until at some point it's able to actually escape out to infinity. So right now we're looking at a top-down view of the accretion disk, and this neutrino is largely trapped in the accretion disk until some point it gets above the accretion disk and is able to escape to infinity. And then, of course, this is for a half dozen trajectories, but you do this 10 to the 12 times, and you get a good idea of what the radiation field looks like. So this is just a simple example of this is the energy density of the neutrino radiation. The problem with this is that it is really, really expensive. So there are a couple of groups that are starting trying to use Monte Carlo transport in multi-dimensional relativistic disks, but it is, like I said, very expensive. And so really what we would like to do is use a more approximate method that and make sure that the approximations are suitable so that we get out everything that we need. So one of the very attractive methods for doing this is something called moment transport. And the idea behind moment transport is rather than discretizing the distribution function into particles, you instead describe the energy density everywhere and the flux everywhere. So you can, so the discretization instead of into particles is into these moments. This is a complete basis, so there's an infinite list of these moments, and formally to describe an arbitrary distribution, you need some amount of every one of these moments out to infinity in order to fully describe the distribution. But the approximation from this moment transport comes in saying, I'm only going to explicitly write the evolution equation for the energy density and the flux. And so for instance, this is the relativistic evolution equation. Everything but the E, the F, the P, and the M, these are all just metric quantities that have to do with the space-time. And so, but the important feature is that how the energy density changes depends on the flux, it depends on the pressure tensor, and it depends on this rank 3 tensor, which I don't have a picture of, but it's just the next term in this expansion. And similarly, the flux depends on the pressure and this rank 3 moment. And so where the approximation comes in is you could write down an evolution equation for each one of these, and they will continue depending on the next term in the sequence. And so you say that's enough, you cut it off at some point, and you evolve the energy density directly, and you evolve the flux directly, and you pretend you know what the pressure tensor and these higher rank moments are. And the advantage of this is if you do guess right, if your closure is perfect, then your evolution of the energy density and flux is exact. And so that's great. But of course, I mentioned it's too good to be true, because they're unfortunately it's very difficult to figure out what that should be, and I'll show why. So to make this efficient, what's generally done is in order to guess what these higher rank moments are, people say, well, I know what the pressure tensor is in the case of a completely optically thin limit, because all the radiation is moving in one direction. And so it's very easy to say that the pressure is the same thing as the flux because all the radiation is moving in one direction. It's pretty simple. In the optically thick limit, you know that the radiation is perfectly isotropic in the co-moving frame. So you know what the radiation field looks like in both of these limits, and you can use the flux to guess whether you're close to the optically thin limit or the optically thick limit, and just do some simple interpolation between them. And so you just say that your pressure tensor is some interpolated value between thin and thick. And this works pretty well in one-dimensional core collapse supernova simulation. So this is a result from a couple of years ago where we did some comparison between moment closures and the Monte Carlo solution. The Monte Carlo solution is black. The moment closures are these dashed lines, and they work within a couple %. And so in one-dimensional spherical systems, in most cases these actually work decently well. But if we look at a neutron star merger, the geometry is a lot more involved. So again, here we're looking at a side view of the disk. So this wedge here is the accretion disk. I forget whether it's coming toward us or going away from us, but the other side is the other side. So it's spinning around. And this region up here is the polar evacuated region. What the colors here are is this Eddington factor. So this is a ratio between the pressure in the direction of the flux and the energy density. So in the optically deep limit, when everything is trapped, we know that this should be 1/3. And in the optically thin limit, where everything is moving in the same direction, this should be 1. And so those two limits match just fine. The problem is in all this intermediate part, where it's you really want to know what the pressure looks like in terms of the flux. So since we have the Monte Carlo solution, we can apply these guesses to it and see whether the Monte Carlo solution matches what the approximate closures what the approximate closures say. And so that's what I'm showing on this bottom panel here. So this is a histogram of all of the grid cells in the simulation. And if it's a darker color, it just means there's more cells that have say a flux factor of 0.2 and a Eddington factor of 0.4. And so you see that most of the cells follow this trend here, and each of these lines is one of these approximate closures. So one of these closures says that for a given flux there is a pressure tensor, and so they generally follow the average trend pretty well. But it's clear that none of these individual lines can possibly account for all of the scatter. So there's a lot of places in here where this approximate closure really just doesn't work. So the goal then would be to say, well, I have all this Monte Carlo data. Let's see if I can improve this closure so we get a good closure while at the same time getting all the speed up benefits of just doing moment transport. So yeah, the conclusion from this is just that moment transport is promising, but the closures are a source of approximation. So before we look at individual closures, I want to look at I want to look at assumptions that don't depend on any particular closure. So for any of these schemes, one of the assumptions is that the pressure is a function only of the flux, and we just talked about this, where there's this giant spread. But even without the giant spread, if you were to say, well, maybe I only want to track the average part, well, there's clearly also multiple branches. So it's not like right here. It's not, you can't use one closure to represent both of these average values. So yeah, the upshot is that no closure fits everywhere on the grid. The second assumption is that the pressure is largest in the direction of flux. So you can visualize the pressure tensor at any location with something like a spheroid, where the size of the sphere in any direction indicates the pressure in that direction. So in this case, there's a large pressure in the direction of this arrow and a smaller pressure in the other directions. And so this is what well, I'll talk about oblateness and prolateness later. But so naively, what you would expect is that if all the radiation is moving in one direction, then the flux and the pressure are in that same direction. And so one of the basic assumptions of all of these closures is that the pressure and the flux are aligned. And what I show in the top panel here is the difference between the pressure in the direction of the flux and the largest component of the pressure. And so this mismatch is a measure of how far misaligned the pressure and flux are. And so that this misalignment is, order of 20%. And you can go and say, well, how well does it relate to all the other directions? And if you say that the flux has to be either in the direction of the largest pressure or the direction of the smallest pressure, then it works okay. But yeah, all the closures on the market assume that the pressure is lined up with the flux. So this doesn't work well in mergers. The third assumption is that the pressure tensor is prolate. So going back to this picture of the radiation field as a spheroid, if it's prolate, the pressure in one direction is larger than the pressure in the other directions, and if it's oblate, the pressure in one direction is smaller. And so all of these closures assume that the pressure tensor is prolate, which would mean that if those assumptions were true, this entire block would just be pure purple. But of course, that isn't true. In a lot of these regions, it deviates very strongly from this prolateness. And especially for these intermediate colors, that means that the pressure in 3 different directions is 3 different values. And so there is no simple way to express that. And the final assumption is just that, so I mentioned that you need to write an expression for the pressure tensor and this rank 3 tensor. And so the temptation is to say, well, I'll just use the same relationship between them because it should be similar. You're interpolating between 2 limits anyway. And the result for this is the same as for the rank 2 tensor. It has the same problems where the closures approximately follow the general trend, but none of the closures is able to encapsulate all of everything that's happening. So then the question is, how can we use this information to provide a better closure? And the conclusion I came to after a good amount of searching is that I couldn't find a way to, in a simple, straightforward way, use any of this extra information to robustly provide a closure, an improved closure for neutron star mergers. So I tried using other information like the density, various other patterns in the radiation field, and nothing seemed to work well everywhere. I thought that maybe the quantum degeneracy of neutrinos had something to say about it. So I extended the maximum entropy closure for Fermi Dirac radiation. I extended it to a rank 3 moment, and as you can tell by the slide, the rank 3 moments did not have a terribly large impact on, or the modifications to the closure did not help matters very much. So unfortunately, I was not able to find a way to use this information to provide a better closure. So it seems like, as I was complaining before about this being too expensive, I think the upshot is we just have to deal with it. So yeah, the conclusion here is that 3-moment closures are likely to little benefit the transport, and we're in a situation stuck between balancing approximations and cost. All right, so that's it for the neutrino transport. Before I go on to flavor physics, I wanted to ask if there were any questions on this part.
I just had a short question, just to get a feel for the numbers. What's the mean free path of a neutrino, roughly, in the kind of conditions you've been looking at?
I don't actually know. Let's see, so the typical cross-section is something like 10 to the minus 44 square centimeters. So, oh no, I'm trying to do this on my head, and that's not going to work. Okay. It's very short, sub centimeter, but
yeah, okay, that's what I'm looking for. Just the kind of order of magnitude. So the neutrinos actually stay in the accretion disk for sufficiently long time. What would be the time scale roughly? Then they would be, sort of confined to the accretion disk.
So the accretion disk is actually not terribly bad. It's the hypermassive neutron star that's really difficult. So yeah, the accretion disk is relatively it's never very, very optically deep.
Mm-hmm. Okay. Good. Thanks.
So Sherwood, I have a question. There's the discussion you had basically says that the pressure tensor and this third rank tensor is very complicated, but at least as far as we know, in core collapse supernovae or in neutron star mergers, the momentum transfer is not that important, like the pressure from the neutrinos, right? It's just the energy exchange, right? And so have you looked into whether just ignoring the accuracy in higher moment tensors really changes a lot the rate of exchange of energy, or is it all coupled in such a way that you mess up in the higher order tensor and your 0th order exchange is affected?
Yeah, I think that's a good question. And so I think you're exactly right, where the pressure tensor in this application doesn't matter for any of the heating or cooling directly. The problem is that the rate of change of the flux, say, depends on a gradient of the pressure tensor. And so it's that spatial, the spatial flow patterns that depend on the gradient of the tensor rather than the interactions themselves. So the classic example is, for instance, if you have an accretion disk where there's a bunch of neutrinos coming from the hot inner part of the disk and convening in some area above the disk, what you would expect is these neutrinos pass through each other and interact with stuff on either side. But what these analytic 2-moment simulations show is that the neutrinos come up, and because you only have one flux direction, you only have one pressure direction, so they come up and they just all go straight upward rather than passing through each other. So if you're ejecting matter from off the accretion disk, it's easy to imagine that matter might not be interacting with neutrinos correctly because neutrinos aren't flowing in this transparent region correctly.
Okay, so it's the directionality of the beam basically that's messed up when
Right.
you have the, okay, yeah, I understand. Thank you.
Yep. All right, so I will talk briefly about neutrino flavor transformations. Maybe, okay, I'll skip most of the history just for time's sake. But so in neutrino transport, the way we treat neutrinos is we say there's, so this is a chart of the standard model of particle physics. And so there's 3 different types of neutrinos called flavors for I don't know why. And they correspond to 3 different kinds of leptons. And each of these neutrinos has no mass. And you know, if an electron neutrino is born, it stays an electron neutrino. But in reality, neutrinos are a little bit more identity fluid. They can change between electron neutrinos and muon neutrinos and tau neutrinos. And so that the proper way to describe this is instead of an individual particle, is each neutrino is a quantum superposition of multiple different flavor states. And so you can describe that with a quantum density matrix. And it was only a couple of years ago that the full equations that describe this was actually reasonably fleshed out. Yeah, so I'll skip that, and I'll just say that there has been some back and forth, some confusing back and forth over recent decades in the core collapse literature that so oscillations were proposed and were proposed in the 60s and experimentally confirmed in the early 2000s. But then the theorists said that, well, we expect that because neutrinos are passing through matter, they feel the effect of the electrons around them, and that effect will affect one flavor more than the others. And so you lock it into a flavor state, and you're not actually able to transform flavor in a way that would modify any of the supernova or merger dynamics. But then theorists said, well, actually, neutrinos aren't only passing through matter, they're passing through other neutrinos. And so this neutrinos feeling other neutrinos change, so the neutrinos change their flavor, which changes how they change flavor. And so it's a nonlinear feedback problem, which is very, very rich. And then people carried out some of the first resolved neutrino oscillation calculations and said, well, yes, this happens, but the oscillations only happen outside of the shock. So in the case of a supernova, it doesn't actually affect what the supernova does. And now we're on the flip side of that, where there's this so-called fast flavor instability that if you get your neutrino distributions in, if you get the right situation for the neutrino distributions, you're sensitive to a very rapid instability that causes the flavors to change in a matter of nanoseconds deep inside of the shock. So I will just show, I want to talk about other stuff. I don't really have time for discussion. So I will just, for this, I will just say that there are interactions, neutrino interaction rates that are calculated for, for decades for core collapse supernovae. And we now know how to turn these into the quantum kinetic matrix terms without doing any extra integrals. So we know all the collision terms and we know how to treat all the equations. And the difficult part of this is the time scales. So this is a particular choice I just started. I'm pretending that the neutrino distribution stays isotropic and it's in a density of 10 to the 12 grams per cubic centimeter. And I start the quantum state off. So it's a combination of muon and electron neutrinos with with a large off-diagonal component saying they're quantum mixed. And if you don't have oscillations, there's some time scale that the collisions re-equilibrate this to sap off those off-diagonal elements and just return it to a pure electron and muon flavor state. And that happens over hundreds of microseconds in this case. The problem is that for the oscillations, this occurs on a matter of picoseconds, or a fraction of a picosecond. So the oscillations are much, much faster, which means they're numerically difficult to treat. So So we have, this is another open source code that simulates this physics, assuming an isotropic background. And it looks something like this. So on this, this panel right here, this is showing the matrix that represents the neutrino distribution. So this represents the on-diagonal element. Yeah, so this is the number of electron neutrinos. This is the on-diagonal element that shows the number of muon neutrinos. And these wings on the side are the off-diagonal elements that show the quantum mixing between the two flavors. And so you see that in the center, there's these rapid oscillations. It's just a line being drawn that completely fills in the space. So that's the flavor oscillations occurring at these picosecond timescales. And on top of that, since collisions are occurring at the same time, over a period of many, many oscillations, the collisions change the way these oscillations are happening. They change the amplitude of the oscillations, and they tend to drive the distribution back to this, this flavor eigenstate denoted by a 1 here. And if you're more comfortable with looking at quantum states for electron spin, it's actually entirely analogous, where you have a, this is like a block sphere. So if the vector is pointing straight up, it's spin up electron. If it's pointing straight down, it's spin down electron. And if it's somewhere in the middle, it's a quantum superposition of them. It's exactly the same math for the flavor, except there's, in reality, there's 3 flavors rather than 2 spins, but it's functionally the same.
Something happened to the, it's all chopped up on mine.
What's all chopped up?
The slide, the fonts. Is that true for other people?
Yeah, the resolution has kind of gone down for some reason.
Huh. What if I pause it? Is it visible if it's paused?
No, like I can't read those letters on the left there underneath the sphere.
What you could do is stop sharing and then sharing again. That might fix it.
All right, let's see. How's it look?
Yeah, that's great.
Okay. So yeah, I'll leave it like that for a second and let it play through to the end one more time. Yeah, so this is the analogy of the block sphere, and it's open source. I should change this. It's now published. It's not an archive anymore. But does the video work?
Yep.
Okay, cool.
Yep.
Yes. So yeah, very different timescales for the oscillations and the collisions. So yeah, we have this code that can simulate flavor change and collisions at the same time. This is assuming it's isotropic, and we're working on extending this to more dimensions. And you can get the, using this, you can calculate how quickly the quantum decoherence happens. That is how quickly it's pushed from quantum mixed states to separate flavor eigenstates. The last thing that, all right, I'll pull a typical speaker move and say I'm going to take 2 more minutes. So you can do this, instead of pretending it's isotropic, you can do this tracing through a neutron star merger as well. So this is an example of a background general relativistic neutron star merger simulation from Francois Foucault. Each of these curves shows a geodesic in this space. And so these calculations are, I start the calculation at some point and integrate outward. And the color of this curve here shows the probability of some flavor transformation happening. For some of them, they don't do flavor transformation, but for some of them, at some point, there's a resonance that incites a strong flavor transition. And this is due to what's referred to as the matter neutrino resonance. And so at some point, this resonance happens and you get a significant conversion. So this is the number density of electron neutrinos in blue and a muon neutrinos in green. And so it changes significantly once this oscillations happen. If there weren't oscillations, it would still change due to collisions. So this isn't a flat line, it's evolving from collisions along this path, but oscillations significantly change it. Yeah, so the flavor changing and collisions do happen at the same time in mergers. And the last thing to talk about is this, this fast flavor instability. which recently was shown by Meng Wu to be really ubiquitous in neutron star mergers. So this, it was originally proposed as an exciting exploration of core collapse supernovae, but the same physics is true in neutron star mergers. So this is another side slice of the neutron star merger, and you can see that the growth rate of this instability, this instability grows everywhere on the domain. And they also they showed using a guess of what this instability does to neutrinos to show that it really does have an impact on what kinds of elements get ejected from this neutron star merger. And so what we're trying to do now is simulate this physics directly. So in this test case, we have a beam of electron neutrinos moving one way, a beam of electron antineutrinos moving the other way. We know this is unstable, so I provide some sinusoidal perturbation, and you expect that to grow exponentially with time. And that's exactly what happens. So this is the magnitude of this quantum flavor mixing as a function of time. And this is a log linear plot. So this straight line here means that there's very, very clean exponential growth. And then this growth saturates to some saturation properties, but then very quickly, the version of the code we have now develops some numerical instability. So we capture this correctly, but we're still working on getting the code to the point where it's accurate and stable for long periods of time. So the last conclusion then is that in progress is measuring the real impact of this fast flavor instability to understand what it really does to the neutron star merger and the matter that's ejected from it. And with that, I'd be happy to take any questions.
Okay, thank you very much, Sherwood, for this great talk. We have time for some questions.
So I have a question. So that plot from Meng Wu that you showed, do they make some approximation to be able to go all the way to abundances?
Yeah.
To get that two opposite limits, or?
Yeah, they make quite a few approximations. So these calculations are based on a leakage scheme. So they have the effective neutrino spheres for the antineutrinos and neutrinos, and based on that, they create some emission model from these surfaces to calculate the distributions, which they then use to calculate the growth rates. Then what they do is they have some tracer particles that move through these, and anywhere where the particle moves through one of these flavor unstable regions, they assume that the flavor is completely mixed between all three flavors. It's not known that actually happens. It's possible, it's reasonable, but we don't know how good of an approximation that is yet.
Okay, and so the background is static, and the neutrino sphere just have a parametric trajectory, I guess, through the.
They do it for a number of snapshots. I think they actually do some approximate time stepping, but yeah, it's post-processed.
Okay.
I have a question. So in your calculations, if I understand correctly, you're mostly interested in the spatial and the time dependence of the neutrino population. Do you ever care about the momentum distribution?
Yes. So I think related to Rodrigo's question earlier, the momentum distribution can be very complicated. Or do you mean like the magnitude of the momentum or the direction?
No, but I'm just thinking, so you have some, let's say in the Boltzmann simulations, right? You have this distribution function. In general, it's a function of position and momentum in time. Mm-hmm. So my impression was that you mostly do hydrodynamics. So you sort of integrate out the momentum dependence and you track the position and time dependence of the distribution. But are you interested in like the velocity distribution of the neutrinos, for instance?
Yeah, okay, so yeah, I think I see what you're saying. So for moment transport, that's exactly what happens. You integrate out all those details. For Monte Carlo transport, it's the inverse, where that really has all of the nitty-gritty details in it. And so I would actually say that it's a little bit the inverse of what you said. Generally, I don't deal too much with hydrodynamics, and I deal only with trying to understand this detailed phase space of the neutrinos. So yeah, I think that's entirely accurate, that how the neutrinos look in momentum space is just as complicated as how they look in position space.
Okay, thank you.
I have a question. for you, Sherwood. Very nice talk. I really enjoyed the summary
Thanks.
of the different things. So one thing which I wanted to ask is this, in the last part of your presentation on this instability, this fast flavor instability. So I assume it exponentially grows. Is it an exponential growth? And another question is, how does it saturate?
Yeah, that is my question. So yeah, so it does exponentially grow, and that's you can directly measure that in the simulation. The question of saturation is, I mean, that's precisely what I'm working on, because if the instability happens, but really I think what you're getting at is if it causes only very small change in the actual neutrino distributions, then it doesn't actually matter if it's unstable. Like, who cares? But yeah, so to understand that where the field is right now is, so this equation right here that I didn't talk about is a linear stability analysis, and people have derived for a lot of these simple cases and more complicated cases what the growth rates should be. And so what we're doing for the first time is showing that the growth rates that we simulate are exactly the same as what's calculated with the linear analysis, and then going a step beyond what can be done with linear analysis and trying to get at what it looks like after it saturates.
Right.
Yeah. So
yeah, I'm a plasma physicist, so this almost looks like a two-stream instability.
Yes. Yeah. I think it's very related. Yeah.
And normally in those instabilities, in the phase space at least, you get trapping. So you basically get kind of trapping vortices forming. And,
right.
That's one of the major ways these two-stream instabilities typically saturate. But
yeah, and that's like I've seen those simulations where you sort of like you have a flat momentum distribution that starts curling on itself, right?
Right.
And I don't know how to draw the analogy to neutrino physics, because rather than in momentum space, the instability is in flavor space.
Right.
Yeah.
Yeah. Thanks.
Any further questions? Okay, well, if not,
right.
Let's thank Sherwood again for a very intriguing, interesting talk.
Yeah, thanks so much. A lot of fun. Thanks for all the great questions.